So one of the most famous 2-qubit states is known as the Bell pair or EPR pair. This is the state 1 over square root of 2 ket 0, 0 plus 1 over square root of 2 ket 1, 1. It turns out that this state is entangled, so it cannot be written as a product of two single qubit states. But moreover, we say that this state is actually maximally entangled, meaning that it is furthest away from any product state under a suitable notion of a distance, which we won't get into in this course. And because of this property, this state is particularly useful in quantum communication and quantum cryptography tasks. And we will see an example of how special this state is in one of the next modules about non-local games. Now next, I will prove to you that the EPR pair is in fact entangled. It cannot be written as a product of two single qubit states. So suppose that the EPR pair were a product state. We'll make this hypothesis and we will see that it leads to a contradiction. And what this will mean is that the EPR pair cannot be a product state. Okay, so suppose for a contradiction that it were. Then what this would mean is that there would exist two single qubit states, alpha 1, 0 plus beta 1, 1, and a second qubit state, alpha 2, 0 plus beta 2, 1, such that the EPR pair is equal to the product of these two single qubit states. Now, by the way that we have defined this notation of product of two single qubits, we can rewrite the latter as alpha 1, alpha 2, 0, 0 plus alpha 1, beta 2, 0, 1 plus beta 1, alpha 2, 1, 0 plus beta 1, beta 2, 1, 1. Now, in order for the first line to be equal to the third, it must be that each of the four coefficients of the standard basis states must be equal to each other. So there's a one-to-one correspondence, meaning the 0, 0 coefficient of the first line must be equal to the 0, 0 coefficient of the third, meaning that the ket 0, 0 coefficient of the first line must be equal to the ket 0, 0 coefficient of the first, What this means is that the ket 0, 0 coefficient of the first line must be equal to the ket 0, 0 coefficient of the third line, of the second with What I mean by this is that the ket 0, 0 coefficient of the first line, which in this case is 1 over square root of 2, must be equal to the ket 0, 0 coefficient of the third line. What this means is that the ket 0, 0 coefficient of the first line must be equal to the ket 0, 0 coefficient of the third line. Now the ket 0, 0 coefficient of this. What this means is that the ket 0, 0 coefficient of the third line must be equal to the ket 0, 0 coefficient of the first line, and the ket 0, 1 coefficient of the third line must be equal to the ket 0, 1 coefficient of the first, which is 0, etc. Now, to convince yourself that this must be the case in order for equality to hold, if this is not immediately clear to you, think of the two states as four-dimensional vectors, because this is what two qubit states are. They're four-dimensional vectors. In particular, the first line, the EPR pair, is the following four-dimensional vector. It's 1 over square root of 2, 0, 0, 1 over square root of 2. And now the two qubit state in the last line is equal to the following four-dimensional vector is alpha 1, alpha 2, alpha 1, beta 2, beta 1, alpha 2, beta 1, beta 2. And so in order for these two vectors to be the same, each entry must be equal to the corresponding entry in the other vector. And it's quite easy to see that it's not possible for all four of these constraints to be satisfied. In particular, if we look at the second entry, we deduce that alpha 1 beta 2 is equal to 0. And what this means is that at least one of alpha 1 or beta 2 is equal to 0. But notice that this implies that at least one of alpha 1, alpha 2 or beta 1, beta 2 will be equal to 0. Right? If alpha 1 is equal to 0, then alpha 1, alpha 2 will be equal to 0. If beta 2 is equal to 0, then beta 1, beta 2 will be equal to 0. But looking at the first and the last entries of the two vectors, we would need that alpha 1, alpha 2 is equal to 1 over square root of 2 by comparing the first entries in the two vectors. And we would need that beta 1, beta 2 is equal to 1 over square root of 2. And so it's not possible, by what we have deduced, that both of these equalities are satisfied. And so there do not exist any alpha 1, beta 1, alpha 2, beta 2, such that the EPR pair is equal to the product of these two single qubit states.